Good afternoon, everyone. Uh, I'm Sai Sriharsha. I'm sorry for the inconvenience for not being there in the class. My PPT background is not working to record my video, so it's going to be a PPT along with my art, my well as talking. Uh, so the paper is building knowledge graphs from public data for predictive analysis. This is a pretty recent paper. It's published in 2016, and the basically the paper is about uh, predicting future technologies and their locations using the existing data sources which are collected. Uh, and let's go to the abstract. Here, the author proposes a system which look at the research papers and patent records. Uh, Research papers in the sense to have a look at the specific technology, the origin of a technology, I mean the location and the year and the date of the technology, and the system predicts the future scope of those technologies in the particular cities mentioned in those papers, which which are related in those paper, and also compares with the rest of the cities. So the papers presents a end-to-end system that integrates heterogeneous data sources into a knowledge graph in RDF. Like the data which we have, is collected from the different research papers and patent records, are not are in a very unstructured manner. So we need to make them into homogeneous data set uh, build a knowledge graph. So so that the user can query upon the knowledge graph easily to generate the predictive analysis. The author discusses a case study of predicting geocenters of fuel cell technologies, which is a technology specified in those papers, using data collected from public sources. Using this end-to-end system, we can also do for other technologies rather than fuel cell technology only. Uh, so, coming to the unstructured to analytic tasks. Uh, as we collected the data from different sources. With different sources, I mean the author collected few like thousands of IEEE papers and also thousands of patented documents, US patented documents, and these data is taken as our input data. Uh, this data is an unstructured data, so we need to integrate into homogeneous data sources, and the data is mapped to make a unified representation. Then with that representation, we build the knowledge graph, and we generate feature vectors on the knowledge graph uh, through our process, and those feature vectors will be used for doing predictive analytics. So and also the user can easily add a data source and switch between analytic tools to test different hypotheses is also provided in the paper. Coming to the overview, this paper discusses about the end-to-end system which takes public data and creates a knowledge graph, use that knowledge graph for doing predictive analytics tasks. So the system generates a spatio-temporal resolution of a city and year level granularity. What does it mean? It means the real-time analysis of the time versus location. Location. Imagine a graph with the x-axis, time as x-axis and location as y-axis, and the points in the graph will be the technology hubs. So what I mean to say is like if Overland Park is famous for uh, technology cities would be on the graph in the x-axis. Uh, 3 2010 Overland Park on the y-axis, like 1 comma 1 2010 and Overland Park. 2 comma 2 is 2012 and Overland Park. So we can see that a positive slope in the graph from 1.1 to 2.2, which can be predicted. For example, I'm not saying that the system is like a graphical system. I'm just saying for an example's sake. So we can predict the evolvement of technology, like from 1.1 to 2.2. We can say that the evolvement of technology in Overland Park from the previous graph example I stated. Uh, Doing this manually is a pretty tough task. So we need to use knowledge graphs and big data analytics tools, which the system does. So benefit for this system is like is a very pretty much advantage for the investors, because it helps them to choose the profitable geographic locations and filter out irrelevant locations for maximizing the investments. It's like if Uber knows the in San Francisco, they or for example, San Francisco is well known. For example, in Kansas City, there's scope for development for future technology hubs, which means more number of users, more number of people living in Kansas City, which means more number of Uber users. So that investors can invest in Uber in Kansas City rather than Topeka, which does not have future growth for technology. Indirectly, there is no future growth, less future growth for more people, which means less Uber usage. Uh, I hope I'm clear with the explanation uh, of the example. Okay, technology center in the paper, technology center means a manufacturing cluster or a distribution center or a research center. Yeah, this study did not distinguish between a technology center. In all my examples, I consider technology center as software companies. It can be anything like manufacturer and some other things. So the paper deals about this case study. In this case study, the data set is collected from the 2008 to 2013 IEEE papers and also United States Patent and Trademark Office papers, as well as some geospatial data from OpenStreetMap API and also the geo names. Like so we have the data from these papers and we have the APIs which can locate these locations in a location time scale. So we predict the future centers of fuel technologies in the 2014. Like the paper took the data from 2012 to 2000 to 2018, 2008 to 2013, and also USPS trademark data and predicted the future technologies for the year 2014. And also they verified their prediction results using the industry reports of 2014. They can know the error analysis or error rate of their model. Coming to the overall system architecture, like first they collect data, then next they model the data, and then they generate feature vectors for predictive analytic tasks. And this is the predictive analytic systems which we can imagine as a uh, interface like a website or an app. So we collect data from online sources using APIs and the research papers, and we clean the data to make a structured data, to make it into a homogeneous data, and we make an ontology with and to generate a graph, our knowledge graph, and we can query the RDF graph to obtain the feature vectors, and with the feature vectors for training the for training we train our machine, I mean our learning model for doing the predictive analysis tasks. So collection, modeling, feature vector generation, machine learning, and the outputs, which are predictive analytic tasks, is performed in the paper. So collection of data, cleaning of data, and metadata augmentation. Like as the data sources are research papers and APIs and patent records, uh, and also which uh, and also from OpenStreetMap API and names from the geo names, we will remove ill-formatted addresses. Like if the address mentioned in the paper is not correct or not in the structure which we want, which will be removed. And also affiliation information, like if a person X wrote a paper and he's affiliated to this company and he's such and so and so, that information will be removed from our data sets to protect the identity or confidentiality of the writer of the papers or the patent records. And if we collect a portion of collected data that did not contain temporal and geospatial information, like if the author wrote a paper in Kansas City, we also collected a paper from Missouri or Topeka or Manhattan, like that. So after data, we collect the data from Missouri, Manhattan, all the things from this OpenStreetMap API and from the geo names. And after cleaning the data, there were 15,602 IEEE paper instances and 16,000 US patent instances. So this is an instance of metadata of raw data in IEEE paper. We can see the author, affiliations like this and this, and the name of the author. So the raw data has the year of publication, like person X works for Google, his name is person X. We should omit out this affiliation data. Like so, the clean data consists uh, clean data and augment data consists the publication of the year, the city where the author resides, the city to which where the paper addresses to, and the adjacent city which we get from APIs data is considered in the cleaned and augmented data. The affiliated data and author names are removed. Similarly, in the US patent data, we will remove the name and affiliations, uh, affiliations such that we will consider only date when patent was assigned, date when patent was assigned to another assignee, author's location, and the technologist location, and the locations referred in the paper, and also adjacent cities which are related to the paper. Okay, the system uses the OSU administrative boundary. So to generate the adjacent cities from which the paper and the authors reside on the paper talks about the location. So for the key description of adjacent city, we take the coordinates of the city and the name of the city and all the adjacent cities stored in the list of tuples. The first element in the tuple is a city name in English and the second element is city name in local language. So geonames, this API this provides a geographical index that lists the cities whose population over 15,000, and thus if the population of 50,000, it is labeled as a big city. Here is an instance of metadata in IEEE. It is an instance of USPTO. The adjacent cities like the paper city is Torrance, USA. The adjacent cities located using the geo name whose population 50,000 is Lawndale, Redondo Beach, Garden, Los Angeles, etc. For Toyota City, the adjacent cities are these and these, which are contouring our geo names. Data modeling. Prithvi will continue from here, and thanks for bearing with me, and thanks for giving me an opportunity to present in the video format as I'm not available in today. Thank you, TSN Professor.